Hi everyone. So today we're going to be talking about the fundamental theorem of calculus, which sounds like a big deal because it is a big deal. This is a really major idea in calculus. This is kind of the thing that ties together the two halves of calculus, the derivatives and the integrals. And so we're going to get into the theory here in just a minute. I do want to just kind of preview this by saying the fundamental theorem, like I said, is a big idea. It's actually divided into two parts that we're going to explore separately, and then we're going to do a whole bunch of work just kind of practicing and exploring in between those two parts so that we can really wrap our heads around this idea. So be patient with yourself, be patient with the material. I'm not expecting you to walk out of here today being a complete expert on this material. It's just not something that can be taught in a class period. So, do a little bit at a time. Keep working through it until it starts to sink in. You will get this, but you just might not get it after one lesson. Okay? So I promise you we'll spend plenty of time on this. You'll be in good shape by the time we're done. But before we dive into the actual wording of the theorem or any examples or anything like that, I want to just do a quick example with you. Okay? So I'm going to do what's called an integral function. I'm going to define something. I'm going to define a function using an integral. So I'm going to say that g of x is equal to the integral from 0 to x of 2t dt. And so what I'm doing here, we're familiar with this notation. We're familiar with what an integral means, okay? But you'll notice that my variable now is this upper endpoint. So when I say g of 2, what I'm really doing to evaluate my function is take a look at this function and find the area between 0 and 2. When I say g of 5, I'm going to find the area of 2t between 0 and 5, okay? So let's make like a table of values here for what this function might actually look like, okay? And we'll just go, 0, 1, 2, 3. I think that should be enough to make my point. And what I want to do is I need a graph of what does 2t look like. Okay, so 2t is going to be, if this is, your y values and these are your t values, it's going to be a linear function. It's going to look like this, okay? And it'll have the point 0, 0. It'll have the point 1, comma 2, the point 2, comma 4, and the point 3, comma 6. So this is the function y equals 2t, okay? So when I'm looking at this integral function, and I want to know what is g of 0, what I'm really asking is what is the integral from 0 to 0? Well, we know how to work with that, right? If it's 0 to 0, then that's just 0, because that's an area of 0. Okay, what's the area from 0 to 1? That's what this next piece would be. All right, so that's talking about this triangle right here. What is the area of this triangle? Well, my base length would be 1, and my height would be 2. So I'm doing 1 times 2 and then divided by 2 because it's a triangle. And so this area is going to be 1. Okay, what about my area at 2? So that would be this whole triangle, all of this. Okay, so now I have a base of 2 and a height of 4. So I'm going to go 2 times 4 is 8, and then divide that by 2, and that's 4. And I'll do one more. So now I'm looking at all of this area for g of 3, because I want the area under the function from 0 to 3. That's what this is saying. And so my area would be, let's see, my base is 3 and my height is 6. So 3 times 6 is 18, and then 18 divided by 2 is 9. Okay, but now take a look at these values. These should look familiar to you, okay? This looks like another function that you've seen before, all right, where 1 becomes a 1 and 2 becomes a 4 and 3 becomes a 9. If I had to guess, I would guess that if I were to do g of 4, that answer would probably be 16, okay? And if I had to do g of 5, that answer would probably be 25. And if you don't believe me, feel free to pause the video right now and think about what would the area of that triangle look like. Okay, just like what we were just doing. Okay, this is really the x squared function. Okay, you should see 0 squared is 0, 1 squared is 1, 2 squared is 4, and so on. And so this integral function, like we can find an integral of this thing from 0 to whatever, but what we're finding is that our answers always come out as x squared. Okay? So the question I want you to ask yourself now, and when we do this in class, we're probably going to do a lot more examples just for me to kind of, convince you, but for the sake of this video, I'm just going to do this one. What is the relationship? Now, I know I use t here, and the only reason I use t is because I was using x to represent, my endpoints down here. That was where I needed my variable to be. But what is the relationship between 2x and x squared? Okay, we started with a 2x, we did an integral to it, and somehow ended up with x squared. And this should look familiar from the beginning of the year, that 2x is the derivative of x squared. Okay? And so what this integral just did for us is it reversed our derivative. Okay? Is if we think of this function as being f prime, then the integral took us back to the original f of x function. It undid the derivative. Okay? And that is what the fundamental theorem of calculus is all about. So, here's the wording for the fundamental theorem, okay? And this is the first part of the fundamental theorem. Like I said, there's two parts to it. And the second part, I think, is more practical. This is more theoretical. But this is really the big point right here, this one that I put the star next to. Differentiation and integration are inverses of each other. They undo each other. They are reverse processes. If you have a function and you want to know, like, hey, what is this a derivative of? Then if you take an integral function, that's going to take you back to what the original function was. So if you have a velocity function and you do an integral, that's going to take you back to a position function. Okay? So integrals help you like reverse course on derivatives. Okay? Now, what this first part of the fundamental theorem is saying, it's kind of confusing, but if you have an integral function, so notice my integral function, it starts at a, but a can be any number. The one we did just a second ago, I was starting at 0. But if your integral function is designed where you're going from a number up to x, okay, of some function, all right, and then you take a derivative of the integral, okay, so I want to say that real carefully. If you take a derivative of the integral function, what this is saying is the derivative and the integral cancel each other out, and you're just left with the original f of x. Let me show you that in terms of the example we just talked about. So if this is my integral, okay, this is my integral function, and I come along and say, you know what, I want to take a derivative of this thing. I want to take a d dx, okay, so I'm now taking a derivative of this thing. Okay. Well, this is just going to be, we use g of x, but this is really y. So we can say this is dy dx. And then, okay, so what I'm really learning today is how do I take a derivative of this function? But we said a second ago that this function could be rewritten as x squared, and we know what the derivative of x squared is. The derivative of x squared is 2x. So that's my answer. Okay, and so look at what really happened. This function that I started with, this 2t, all that really happened is this x dropped down in place of this t, and that was my answer. Okay, so I'll just throw another example down here real quick. If I had an integral function, I'll use a y just for the sake of notation. If my integral function was from 5 to x of 4x cubed dx, and I said, hey, I want the derivative of that thing. Okay, well, the derivative and the integral are going to cancel each other out. Oh, and you know what, I'm sorry, when we write these, we don't put the x in both places here, so this should be like a t, or it'll be some other letter. Okay, But when I go to take the derivative and the integral cancel each other out, and all that's going to happen is my answer will be 4x cubed. Okay, that's it. That's the math that you have to do today. And we're going to talk about some like different scenarios that can happen with that. But that's the idea, is that when you take a derivative of an integral function, we're just going to add this to the list of all of our derivative rules. When you do a derivative of an integral function, derivative and integral cancel each other out, and all that's happening is the x, that independent variable, is going to come down in place of the t or whatever other letter might happen to be there.
Okay, so now let's apply what we've been talking about with the fundamental theorem of calculus part 1. And remember, this is all about taking derivatives of integral functions, which is exactly the setup I have here. I have an integral function starting from a number and heading out to x, where that's my independent variable, and I'm trying to take a derivative of this thing. So in this scenario, this is the easiest one of these you're going to run across. To do a derivative of an integral, those two things are just going to cancel each other out. And this x up here is just going to drop itself into the function. So my answer for my derivative of this function would just be cosine of x. Okay, that's really all there is to it in these scenarios where you're doing a derivative of an integral. So in example 2, well, I guess, sorry, this is still part of example 1, but in this problem here, it's the same setup where I have a derivative of an integral, but I want you to notice that the endpoints are a little bit backwards from what we had before. Up here, I had a number on the bottom and an x up on the top. This is reversed, okay? But that's okay. We know how to work with integrals that are reversed. All that's going to do is make my answer negative, right? Because we really want to think about this as going from 5 to x instead of x to 5. But what that's going to do is negate my answer. So I'm going to throw a negative in there. But other than that, the same thing's going to happen. The x is just going to go up and live inside this function. So it would just be x minus 3 squared. Okay, these can get a little trickier, okay? It's all stuff you've seen before. We're going to just kind of mix some new things together here. Sometimes you are starting from a number, but instead of going up to just a plain x like this, you have some other function of x. So maybe it's an x squared or a 3x or some expression involving x. So just like before, we're going to take this thing and we're going to drop it inside this function. So part of my answer is going to be f of g of x. But then now we're taking a derivative of something that has a function inside of a function. And if you think back to when we did derivatives, we had to do something special with that. And that would be the chain rule. So I'm going to do this. I'm going to drop this in, but I'm also going to multiply by the derivative of this g of x. So I'm going to say g prime of x. Sorry, trying to cram that in there. See if I can write that a little better for you. I'm going to say g prime of x times f of g of x. So then what happens if I have functions on the top and the bottom? Well, this kind of ties into the second part of the fundamental theorem, which we will get to later on this week. So for right now, you might just have to take a little leap of faith with me. We're going to do the exact same thing we did here. So I'm going to take the g of x, I'm going to drop it in, and I'm going to apply the chain rule. I'm going to say it's g prime of x times f of g of x. But then we're going to take and subtract the same type of expression with the h of x. So we're going to say minus h prime of x times f of h of x. And the explanation for that really involves the fact that like we're taking the difference between the two areas to find the area in between these two functions. So but I'm going to kind of skim over that for right now because I do think that'll sink in a little bit better once we get to the second part of the fundamental theorem. So, okay, two more examples here to do real quickly. And of course, it's one of each of the things we just talked about. So this one is going from a number up to x squared. So, and I'm doing a derivative of an integral. So again, I'm going to see this happen, right? Derivative and integral are going to cancel each other. The x squared is going to hop down here into the sine function. So I'm going to end up doing a sine of x squared. But then by the chain rule, I need to multiply by the derivative of x squared. So I would just say 2x times sine of x squared. With my next one, I've got two different functions, top and bottom. So I'm going to start by dropping in the x squared, and that's going in place of the t, because that's my variable placeholder. And I'm going to multiply by the derivative of x squared. So I'm going to say 2x times 1 over 2 plus e to the x squared. And then I'm going to subtract and then do the exact same thing with the 2x. So I'm going to say derivative of 2x is 2, and then take the 2x and put it here. So 1 over 2 plus e to the 2x power. And I'm just going to leave it like that. I mean, the only other thing I could do is I could take these things and put them up on top of the fractions, which would be fine. But I can't combine anything. I don't have like terms or anything like that. So that would be as far as I could go. So that's my answer. That's my derivative. Okay, that's all you really have to be able to do today. So really today is just about taking these things and placing them in the function correctly and understanding this idea that a derivative and an integral cancel each other out. There are much bigger ideas at play here that we will continue to kind of circle around the rest of the week. But for today, if you can handle this stuff, you should be in good shape.